the work kinetic energy theorem. So, a very important theorem in physics, and we'll be using the work kinetic energy theorem really anytime we problem solve problems from now on. And I have a short derivation of it to show you here. It's very short. I think it's very understandable, and will give you a better satisfaction and understanding when applying it to problem solving. So let's take a look. We have a force F, and for purposes of this discussion, we're going to assume it's a constant force, but we'll see the work kinetic energy theorem applies even if it's not a constant force. But we can get a very quick derivation just by considering the constant force. And if that force is acting on a mass, Newton's second law certainly applies. So that's my Roman numeral equation 1 here, F equals ma. If it's a constant force, then we can apply the constant acceleration equations, and that's my Roman numeral equation 2. So to see our derivation and how the kinetic energy for an object is defined, we are going to take equation Roman numeral 2 and solve it for delta x. So just do the algebra to solve for delta x, get it by itself, and we have this v final squared minus v initial squared over 2a. Well, we are going to substitute that in for delta x in our f dot delta x equation. Since our force is only in the x direction in this problem, we are taking the ma up here and plugging that in for f of x. So I guess I did it in green. So this is the force fx equals ma. So our delta x comes in for the delta x, and believe it or not, that is it. Voila! Of course, the cosine, getting a little ahead of myself, cosine of 0 degrees here when we do our dot product, because the delta x is forward, the force is forward, so that's where we get our cosine of 0 degrees from. And now, voila, we are here. We have the work done by this force can be put in the form of 1/2. So we have the 1/2 mv final squared minus 1/2 mv initial squared when we distribute the m through and put the 1/2 outside. Well, that is it. That is our expression for kinetic energy. So kinetic energy, by definition, is just equal to one of those terms, the 1/2 mv squared term. So we have instead of constantly referring to it as 1/2 mv squared, we say kinetic energy. So 1/2 mv final squared would be the final kinetic energy of the object. 1/2 mv initial squared is the initial kinetic energy. And notice then the work done on the object equals the change in the kinetic energy of the object. And that is the work kinetic energy theorem. So if you are asked, what is the work kinetic energy theorem? You are simply going to read this equation. So you do not want to get fancy with trying to come up with other language or other words. You will simply read the equation. So the work kinetic energy theorem says that the net work done on an object, and please add the word net, that's important, the net work done on an object equals the change in the kinetic energy of the object. 1/2 mv final squared minus 1/2 mv initial squared. So that's it. I have a short aside over here, but it's really interesting, so I want to take a moment to introduce another very famous energy equation that is eerily similar to what we just did. Why so similar? And that's the question. Why so similar? Without very much deep knowledge of physics, a few chapters of introductory physics, we could come up with an equation, that says energy equals 1/2. 1/2's a constant, so let's just leave that there, but ignore it as far as our discussion is concerned. It's just 1/2. Energy directly relates to mass times speed squared. And E equals mc squared is Einstein's famous equation that he's very famous for. But he is not famous for just coming up with an equation that said energy is directly related to mass and speed squared. That was well known prior to Einstein coming up with his E equals mc squared equation. So why is Einstein famous? And he is rightfully famous for this equation. First of all, the speed is not any speed. The speed is the speed of light. Now, Einstein did not determine the speed of light. The speed of light was known prior to Einstein's formulating this equation. The E in his equation is the energy of light. Now it's getting to be important because we have an equation that allows us to calculate the energy of light. But if you really want to understand why this equation is so important, it's because if E is the energy of light and C is the speed of light, what do you think M is? Well, if you said light, you are correct. So, what? Light has mass? I'm going to put it in quotes. Mass of light. Well, light, as it turns out, is pure energy, but it has what is called a mass equivalent. And this equation allows us to calculate the mass equivalent of a certain amount of energy, or conversely, to take a given amount of mass and calculate the total energy contained in that mass. That's why Einstein is so famous and why this equation is so significant. And we'll talk more about that in class as well. But I wanted you to have that in your notes, and I thought it was fun just to introduce right away as soon as we have an equation that shows us energy is related to mass and speed squared. Okay, so one last page here. This is just a repeat of the work kinetic energy theorem, but there are some very important notations here as far as getting questions right for the AP tests or even for our tests. So the work done, and again, it's the net work done. I really should have work done. Please make sure you put in there net equals the change in the kinetic energy, still equals F dot delta X, where F there would have to be F net as well. F net dot delta X equals the change in the kinetic energy. The V's in this equation are speed, so they're not positive. Kinetic energy is not positive because we're squaring the velocity. We don't square velocity. It's speed squared, and speed is always positive. Anyway, kinetic energy cannot be negative because the least amount of kinetic energy you can ever have is 0. An object can't be moving slower than stop. So the speed of an object can never get less than 0. It either has some speed or it doesn't, and if it doesn't, then it has no kinetic energy. So individual kinetic energy can never be negative, can be 0, but not negative. Now, the change in kinetic energy can absolutely be negative. If you have a negative change in kinetic energy, what does it mean? If you have a negative change in kinetic energy, it means that your initial 1/2 mv squared was bigger than your final 1/2 mv squared, and you'll get a negative change in kinetic energy anytime that occurs. And that simply means you're slowing down. If your 1/2 mv initial squared is bigger than your 1/2 mv final squared, you are slowing down. So delta Ke can be negative, will be negative when an object is slowing down. Well, let's see. Take a look at a quick example here. What if we bounce a ball off of a wall? It hits the wall with a speed of 5, but only bounces off with a speed of 4.2. And these are the velocity that I indicate. The speeds are 5 and 4.2. It bounces backwards, so that's why the negative is here, and it was thrown forward, so that's why the positive is here. Notice when we take the change in the kinetic energy, we only use 4.2 and 5, and notice we do get a negative value because our V initial was greater than our V final. So what's the meaning of this 11.04 joules? Well, that was the energy that was lost when the ball impacted the wall. When the ball impacted the wall, anything that we would observe would be energy lost, meaning if you heard the ball hit the wall, right? If you heard sound, that sound is energy. It's vibrating the air molecules. Those air molecules, that pressure wave goes to your ears, and you hear the pop when the ball hits the wall. That's energy that's taken away from the rebound. Even the compression of the ball, if you had that slow motion camera and saw the ball compress and then expand when it came off the wall, you would see the ball heat up. That compression and expansion would not be perfect. That heat up would be energy that would be part of this 11.04. And if you had a thermal imaging camera on the wall, I'll bet you would see a hot spot where the ball impacted the wall and then bounced off of the wall. So anything that you hear or see is going to be part of that collision with the wall is going to be energy lost to what the kinetic energy or speed of the ball can be when it bounces off of the wall. If the ball had bounced back with a speed of 5, first of all, you have the world's best, most bouncy ball that can ever be. And at that point, you recovered all of the energy. All of the initial kinetic energy was recovered into the final kinetic energy, the one when I would take V final as 1/2 mv squared. But notice that also means no net work was done. So whatever work was done to stop the ball from going forward was put right back into the ball when the ball bounced in the opposite direction. So we're going to be looking at some homework questions, multiple homework questions using the work kinetic energy theorem, as well as talking about some more examples in the notes.